All right, so last video of the week, we're going to get to weak acids. I'm going to introduce the idea, we're going to throw it into an ice table or two, and then we're going to just practice this a whole bunch is really where this is going, because this idea, we worked on ice tables and KEQs in order to kind of introduce this idea. We've talked about acids and bases and concentrations of H plus and OH minus and all that other stuff, and all of that is going to come together in the next 10 minutes or so and be one big thing. So this is definitely an idea that requires practice. So this is your introduction to it, but definitely make sure that you are finding the practice on these things and getting comfortable with these types of calculations. All right, weak acids. All right, so what do we know about weak acids? We know that they're going to have a small KEQ, right? And so in our Bronsted acid base reaction, when we have acid plus water, we're going to create a very small amount of hydronium ion, right? And so we're going to get a small amount of this. So now we need to really think about how small is that amount, and the way that we kind of have in the past, the way that we've made sense of how much of these products do we get out is through the KEQ expression. And so I'm going to write out the KEQ expression here, but I'm not going to quite label it like that just yet. So we have the concentration of H3O plus, or I guess the concentration, I'm going to make this the concentration of H plus actually. The concentration of H plus, remember that H plus and H3O plus are the same thing, times the concentration of the conjugate base all over the concentration of the acid, right? And now we're not including water because water is a liquid, it's a pure liquid, it's not something that we need to include in there. This, when we take the KEQ expression of an acid-base reaction like this, we call this the Ka value. So this is, of course, the acid dissociation constant. It's just another version of KEQ. There's no difference really in how we calculate KEQ versus how we calculate Ka. Ka just tells us we're thinking about acids, right? So the stronger the acid is, of course, the more H plus we're going to create, and so the larger Ka gets. So in general, if you get a larger Ka value, that means that you have a stronger acid, right? And that also means, so larger Ka also means that you're going to get a lower pH when you make a solution of that acid, right? So the stronger the acid is, the lower the pH is going to be. Now this is interesting because so now Ka and pH are related. So let's say that we have Ka is related to pH. So I say I have for you an 0.10 molar solution of a weak acid. And you measure the pH, and well, the pH equals 2.38. The question is, what is the Ka? And how do we figure that out, right? So we know what Ka is. Ka is the concentration of H plus times concentration of the conjugate base, all divided by the concentration of the acid at equilibrium, right? We know what the pH is at equilibrium. And so this is kind of sneaking in here. We're giving you an equilibrium concentration. We have an initial concentration here. We have an equilibrium concentration here. You guys see where I'm going with this, don't you? I hope so. We got to make an ice table. Initial, change, equilibrium. We have our acid. We have our H plus, and we have our conjugate base. Okay? So our acid initial concentration is 0.1 molar. Our initial H plus concentration is 0, initial concentration of conjugate base is 0, because of course these are our products, and so we assume that we start at 0. We know the equilibrium concentration of H plus, right? 2.38 equals negative log of the concentration of H plus. And so if we solve this for the concentration of H plus, we bring the negative over here and then raise everything to the exponent of 10. Because we're using log base 10, we get the concentration of H plus equals 10 to the negative 2.38, right? So the concentration of H plus in general, where do I want to write this? I'm going to put it here. The concentration of H plus in general equals 10 to the negative pH power. So whatever your pH is, that gives you the concentration of H plus in this formula. So this is probably a formula worth remembering as well. It's the same formula as pH equals negative log of H plus, it's just in a different format. Okay. So 10 to the negative 2.38, that's our equilibrium concentration here. That means we can figure out our change, right? So you guys all know how this goes. Plus 10 to the negative 2.38, plus 10 to the negative 2.38, minus 10 to the negative 2.38, right? So our reactants we subtract, our products we added in. Now we can fill in our equilibrium concentration, 10 to the negative 2.38. And over here we have 0.1 minus 10 to the negative 2.38. Now this number is so small that we're going to just ignore it. Now that feels like cheating, right? It really does, because we went through this whole thing of solving all these quadratic equations and previous ice tables and all of that, and now we're just like, nah, we're not going to subtract the change out of this one. And it's cheating. But because it's a weak acid, that number will always be super, super small, right? There's no way around it. And so when you do that subtraction, when you add the change into the initial, it's not going to change it enough, and our Ka value is going to stay pretty much the same. So we just skip it. And we just say the initial concentration is more or less unchanged because KEQ is so small. So now we have equilibrium values for all these things. And that's what we want because we can plug those into our Ka expression. And so now Ka equals the products 10 to the negative 2.38 times 10 to the negative 2.38 divided by 0.1. And we plug all that into our calculator and we get a Ka value of 1.8 times 10 to the negative fourth. Okay. So that's our Ka value. So if we know the pKa, 2.3, or pKa, if we know the pH, I got ahead of myself. If we know the pH, we can figure out the Ka value, right, by using an ice table. And this is actually a pretty straightforward ice table if we know the pH, because everything is just, we only need this number, 0.1, and this number, the pH, and everything else just kind of follows from there. So again, not that terrible, right? Let's make it slightly more interesting. Let's say that this time I say, well, here's a 0.3 molar solution of acetic acid. And so now you can go look up the Ka of acetic acid, but don't, because I'll just tell you what it is. It's 1.8 times 10 to the negative fifth. Okay. What is the pH of this solution? And now I've hidden all of your pH meters, any litmus paper, or any of that other stuff. And so to figure this out, we need, again, an ice table, right? But where you have a different set of values to put in here. So acid, H plus, conjugate base. So we have an initial solution of the acid. These are all 0. We don't have a value, but this is the one that we want, right? We want to know what's our equilibrium concentration of this. And we know what the Ka value is. And of course, we know what the Ka expression is because the Ka expression is always the same. So Ka equals the concentration of H plus times the concentration of the conjugate base all over the concentration of the acid. Okay. And that equals 1.8 times 10 to the negative fifth. So now we need values in these equilibrium things. We don't have any changes that we can figure out, so we have to use X. So this value is x, this value is x, and this value is 0.3, right? Because we're cheating, right? We're just ignoring the x value because the x value will be very small because acetic acid is not a very strong acid. Okay, so once we've done that, now we have equilibrium values. We can plug those in. Now we plug those in here. Our Ka equals concentration of H plus is x times the concentration of conjugate base is x, all divided by 0.3. And that equals 1.8 times 10 to the negative fifth. And now we solve it, right? So x squared over 0.3 equals 1.8 times 10 to the negative fifth. That means that x equals, I'm going to just do the solving of it right now, 2.3 times 10 to the negative third. Now that is our concentration of H plus, and this equals the concentration of H plus, right? 2.3 times 10 to the negative third, because that's what we have X as right here. So now to figure out the pH, we have to take the negative log of that value, negative log of H plus. So plug that into your calculator and you should get a pH of 2.64. So we can, if we know Ka and we know concentration, we can figure out the pH. If we know pH and we know concentration, we can figure out the Ka. So isn't that great? So those are the things that we can do to kind of figure this stuff out. That's the first part of weak acids and weak bases. So we can relate Ka and pH through ice tables. And so that's the skill that we're building towards throughout this week. So next week, we're going to make this more complicated, of course. So we've started here, we've used the materials that we already know, and we're going to go on and, of course, make this as complicated as we can. So look forward to that. Practice your ice tables. Make sure that you feel good on the sheets, on the worksheets and stuff that I give you to do Ka manipulations, pH manipulations, all that other kind of stuff. And if you have questions, bring them to class, come to office hours, send me an email, any of those options, whatever works best for you. All right, thanks, have a good week, and I will see you in the next video.